Here we have a projectile motion problem, so go ahead and pause the video to read the question before we get started. The first thing we'll do here is define a positive x and a positive y direction, as well as identify our two moments in time. Moment in time 1, when the water balloon is thrown out the window, and moment in time 2, when it lands at Chris's feet. At moment in time 1, Sandra throws the water balloon out the window with some initial velocity. We're not told what the initial speed is, so let's just use an algebraic expression of v naught to represent the magnitude of that velocity vector. Breaking it down into its x and y components, we know we have an angle of 60 degrees. Therefore, its x component will be v naught cosine 60, and its y component will be v naught sine of 60. We'll put that off to the side for future reference. Now, projectile motion problems can be treated as two mini problems within the bigger problem, an x problem and a y problem. What I always do to set up a projectile motion problem are two tables labeling displacement, initial velocity, final velocity, acceleration, and time in both the x and the y directions. Once I've set up my two tables, I can begin filling them in with the things that we know. In the x direction, we know that the total displacement of the water balloon will be 6 meters. The initial velocity, as discussed before, is v naught cosine of 60. Now, importantly, in projectile motion problems, there is never any acceleration in the x direction. Therefore, as a consequence, the final velocity will be exactly the same as the initial velocity. Finally, we know that the total time it takes for the problem to take place is 2.5 seconds. In the y direction, our displacement, if we look inside the delta notation, really is y final minus y initial. Let's choose to make the ground our y equals 0 location. As such, for y final minus y initial, we will have 0 minus the initial height, so minus h. The initial velocity in the y is v naught sine of 60. The acceleration in the y direction is the local acceleration due to gravity, so negative 9.81 meters per second squared. Negative because it is in the opposite direction as what we have chosen to make the positive y direction. Importantly, in this problem, we realize that the time it takes for our mini x problem to occur is exactly the same as it takes our mini y problem to occur. Therefore, both t's are equal to 2.5 seconds. Okay, great. So now that we have our two tables set up, we can start using our kinematic equations in both directions to solve for any unknowns. Let's start in the x direction, and what you want to do is pick the right kinematic equation that will only have one unknown left in it, so you can solve for it. So let's use an old favorite, delta x equals v naught t plus 1 half at squared. And solving for v naught, we get 4.8 meters per second. Great, so now what we can do is we can take v naught and use it in our y direction problem, because we also had v naught as an unknown in the y direction. Again, using the same equation, this time just in the y direction, we get delta y equals v naught t plus 1 half at squared. Here, however, we have an acceleration of negative 9.81, so we have to be careful about that. And simply solve for h, because now v naught is known from the x direction problem. And that's it, we just solve for h now. So it turns out that the height from which Sandra threw the water balloon was 20.26 meters. Thanks for watching!